Problem 20. A small particle a small particle of mass m, small m, is pulled to the top of a frictionless half cylinder of radius r by a cord that passes over the top of the cylinder, okay, as shown in the figure. If the particle moves at a constant speed, so the speed v equals constant, show that F applied equals to mg cosine theta. Okay, as you see here, F is attached or applied by on the cord. So here, as you see, we have F and here we have T. We have T. Because we don't have a friction or interaction between the cord and the body of the cylinder, in this case, T will be constant at any point here. So here we get T. You know, if we take this system at this point, we have F to the left and T to the right, okay, equals to 0, because no motion. We can say equals to m equals to, anyway, we don't have mass here, okay? We can say F, we don't have mass, F equals to T as magnitude. So here, T equals to F, we can say. Okay, to solve this problem, we can apply Newton's law. The object move in this direction. Let's say like this. Okay. Here we have T. We have the weight like this. We have T, and because the object is on the cylinder, we have the reaction must be perpendicular to the trajectory. Here we have N, M must be vertical, and we have T, okay? Okay, here maybe like this. Because the angle here must be equal 90, and here 90. And you know, if this one is theta, this one is theta, because if you take this triangle, the angle 90 here, we have theta plus alpha equals to 90, and alpha plus beta equals to 90. So beta equals theta. Okay, if you have here beta, theta plus alpha equals to 90 in this triangle, and here we have 90. We can say alpha or beta plus alpha equals to 90, this angle. So if we take the first one minus the second one, we get theta plus alpha minus beta minus alpha equals to 90 minus 90 to 0. Okay, we get theta equals to beta. So this angle is beta equals to theta. Okay, here is theta. Now to solve this problem, we put the components fx, mgx, and mgy. Because we have the line of motion is up, we can say this is the direction of x-axis. So we take, here we have x, and here we have y. Okay, here we have mg, mgx, and mgy. We take this triangle, in this triangle we can say cosine theta equals to the adjacent mgx divided by mg. So mgx equals to mg cosine theta. Now we apply Newton's law. We have x and y. We have in general all the forces applied. We have T plus mgx plus mgy plus n. We don't have friction, okay? Equals to 0. Why? Because the speed is constant. Because v is constant. Now we have t and mgx on the x-axis, okay? As we have the motion in this direction, we take this the positive direction, t in the positive. So t minus mgx in the negative direction, I, n in the positive direction, minus mgy. As you see here, mgy is down, n is up. J equals to 0. So we can write t equals, or t minus mgx equals to 0, and n minus mgy equals 0. T, so t, you know here, t equals to f. E Why? Okay, I will say why here. T equals to F equals to mgx, and mgx equals to mg cosine theta. So T equals to F equals to mg cosine theta. Okay? This is the answer. We have to find this relation. You know, because the chord is massless and we don't have any interaction, so T we must have the same T on the chord. Okay? And as we said here, by applying Newton's law at this point, we have T to the right and F to the left. So minus F plus T equals to 0 anyway, because here equals to MA. M, we don't have a mass of the chord. The chord is without mass. And also because we have a constant velocity. In this case, A equals to 0. So F equals to T. Okay. B, by directly integrating omega equals to integral f dr, we have to use this relation. Find the work done in moving the particle at constant speed from the bottom to the top of the cylinder. Okay. Now we have the object initially at this position, and we need to apply a F because the ball is attached to the cord. We push with F to move the object from the bottom at this point to the top of the cylinder. Okay, so here we have the initial position, and here we have the final position, and by applying work equals to F dr, we have to use this relation. We have to find the work of F applied on the object. Okay. Now, how can we calculate dr? You know, F equals to mg cosine theta. So here we have mg cosine theta here, and we have dr. You know, the angle between F and dr equals to 0 because the displacement dr is a small portion of the trajectory. The trajectory is from this point to this point, like this. This is r. From here to here, we have r, the arc. The small dr here the small dr has the same direction with F because it's tangent, and F is tangent to the trajectory. Here we have dr, and at this point we push with F. Okay, we push with F, and here we have dr, and also at this point we push with F and also we have the same displacement in the same direction. We arrive to this point, we push with F, and also the displacement will be here. So F and R must have the same direction at any point from the initial position to the final position. So the angle between, we can write here integral of F dr. Okay, F equals to mg cosine theta and dr. Okay, dr is a small portion of the trajectory. Let's say here we have this one from here to here, or from here to here, any position. Okay, here we have dr. The angle here equals d theta, because a small r will be okay, let's take here, if we have the angle like this, and this one equals to r, here we have theta with the radius r. Okay, you know, here small r equal the radius times the angle. Okay, the same if we have a small angle with a small, here we have d theta with a small arc dr with the same radius. We can say here dr equals to r d theta. Okay, the same form here, small dr equal r is constant times small angle. So we can write here integral of mg cosine theta times r d theta. Now the variable is the angle theta. Okay, here the angle theta. The integral, if we move the object from this point to this point, theta will be from this point to this point. At this point, theta equal to 0, and at this point, theta equals to pi over 2. So the limit of the integral will be between 0 and pi over 2. Okay, because we have to move the object from the bottom to the top of the cylinder. The integral must be limited between these two angles, theta equal to 0 and theta equals to pi over 2. Okay, you know r is constant. If we move the object, capital R is constant, we can put it out of the integral. M is constant. We have G. Okay, we have R, M, G. Inside, we have cosine theta d theta between 0 and pi over 2. The integral of cosine theta equals sine theta. So we get R, M, G sine theta between 0 and pi over 2 equals to r mg sine pi over 2 minus sine 0. Sine 0 equal to 0. We get here r equals, okay, we can keep m g r sine pi over 2 equals to 1. Okay, so this is the answer.